BC Chemistry, Unit 4, Yield and Atom Economy. So in this video, we'll talk about how do we calculate the yield and or use atom economy to analyze organic reactions. Let's start with percentage yield. So in reversible reactions in the equilibrium section, we talked about percentage yield. So just to remind you that percentage yield is defined as the ratio between actual yield and the theoretical yield. So theoretical yield is calculated based on stoichiometry ratios. So if I give you a certain amount of reactant, what's according to the stoichiometry ratio, what's the amount of product that should be there in an ideal situation? And then actual yield is basically the reality. Mostly it's subject to formation of equilibrium or loss of reactants or products or reaction rate. So in organic reactions, rarely do we actually have a 100% percentage yield, because we always lose something in every single organic reactions. The conversion rate is always less than 100%. Let's look at one example. So 30 grams of Prop 2O was oxidized to propanone using acidified solution of potassium dichromate. The product, propanone, was distilled, so it's extracted, and then the mixture that was extracted is 20 grams. So basically 30 grams of Prop 2O produced 20 grams of propanone in an oxidation reaction. What's the percentage yield? Well, first of all, we need to write down the pathway to determine the mole ratio. In this case, that's the pathway, and it's 1-to-1 ratio. Well, actually, in most cases, organic reaction has a 1-to-1 conversion ratio. If you recall that when we first introduced the reaction pathways, we mentioned that organic reactions is about the reaction of the functional groups. So if your reactant only has one functional group that will participate in that particular reaction, then you can almost certain that the conversion rate is 1-to-1, because obviously the rest of the chain, the hydrocarbon chain, will remain the same. They're like the base. You're only basically fixing one part of that entire chain. Therefore, the conversion rate in the end, your desired product, is still mostly that molecule. The only changing part is the functional group part. Okay. In this case in particular, we notice that even the carbon atoms in the reactants and products are the same. So 1-to-1 ratio. Without even writing up the entire balanced equation, we know that it's going to be 1-to-1. So when we're doing calculations of organic reactions, a good understanding of the reaction mechanism will allow us to save a lot of time and effort not to write out the entire balanced equation. Okay, so once we determine the ratio, we can use the molar mass mole conversion equation to determine the amount of reactant supplied. Okay, so we know that they actually give us 30 grams of Prop 2O. So using that equation, we can work out it's 0.5 mole. If there's 0.5 mole of reactant, how many moles of product will be produced? Obviously, that's 0.5 as well. Then, using the amounting mole, this is basically the theoretical yield. The only problem is that it's in mole, right? We're going to convert it to mass so that we can do a ratio. So converting that to grams, that's 29.0 grams. Then lastly, we just need to make sure that that's the theoretical yield, because that's the amount of propanone that should be produced according to 30 grams of Prop 2O being supplied. But in fact, we only have 20 grams as actual yield. So as a result, your percentage yield is 69.0%. In this kind of calculations, I want you to really pay close attention to significant figures. Well, you will also notice that for most organic reactions, it's not just going to be a single step process. Normally, to have a desired product, we need multiple steps. So the percentage yield for multiple steps process is simply actually multiplying the percentage yield for each single step, which is normally given. So in this case, A to B is 90%, B to C is 80%, C to D is 60%. Since we multiply them together and have the overall 43.2% from A to D. So basically less than half portion of A are actually turning to D. Notice that overall percentage yield will always decrease because in most chemical reactions, it's not a 100% conversion. Actually, in most reactions, it's not 100% conversion. Okay. So the more steps you have, the more likely you're losing your ingredient along the way, together with other stuff like heat and everything else, right? So chemists normally, we must aim to reduce the steps in one pathway of synthesis so as to maintain a good yield. Atom economy. Atom economy is literally following the atoms in a reaction. So for example, if all your reactants turn into the desired product with no byproducts, it's a high atom economy. So that will happen with addition reactions in most cases. But compared to that, if it's a substitution reaction, you always have a byproduct and a desired product. So the byproduct, in atom-wise, is a waste. We're not really using it. So how do we quantify this kind of analysis? We use basically the molar mass of the desired product, putting over the molar mass of all reactants. And you know that molar mass of all reactants equal to molar mass of all products, because no atoms will be lost in the chemical reaction. So molar mass of all products in this equation will also work. If we don't really have molar mass of all reactants or products, then the mass of desired product over mass of all products will also do. And again, overall mass of reactants will do too. Okay, let's see one example. This is the entire reaction equation, and we are asked to find the atom economy. Obviously, the desired product is the alcohol. So no one is going to go through the entire process to produce salt. Okay, so the alcohol is 46 grams per mole. That's a desired product. And then you have another byproduct that's 58.5. So your calculation of molecular mass, in this case, definitely has to be accurate. Okay, and then atom economy is your molar mass of reactant of the desired product over the molar mass of all products. In a lot of cases, we actually just use the molar mass of all products because we already calculated the molar mass of one product. Might as well just add up the rest of them and put it on the denominator here. So again, overall molar mass of the product should equal to overall molar mass of the reactant, simply because that in a chemical reaction, no atom is lost or disappeared. They just rearrange themselves. So all of them should add up together and equal. So everything beforehand should equal to everything afterwards. So we can safely use the molar mass of all products.